Let me welcome you to the Brian Gill Coe lecture on mathematics in our time. Can people hear me? No. So this is the second in a series of lectures in honor of our late colleague Gill Coe. The aim of these lectures is to show the importance of mathematics and its influence on science, technology, and the rest of society. This year, the Coe lecture is part of the North Carolina Science Festival, which is running this week from the 5th, in fact, for several weeks through the 21st. This festival is the first and largest statewide festival devoted to science, and there's a web page. You should go to it. There are many, many interesting events. Before I introduce our speaker, Martin Golubitzky, I'd like to welcome a few of our special friends, guests, and say a little bit about Gill Coe. Let me first of all welcome Suzanne Gordon, who spearheaded the idea of our efforts to start a mathematics lecture series, and also members of the Coe family, Mrs. Toni Coe and Patricia Friedman and Deborah Coe, Gill's daughters, and his son, James Coe. Thank you, and thank you for your support. You can see more details about Gill's life in the brochure that was handed out, but let me just say a few words about his career here at NC State. Gill came here in 1964, right after receiving his PhD at Carolina, and he had a long and distinguished career here. He published over 70 papers, published a book, and he served as mentor to 11 PhD students. He had a lifelong commitment to education, and he taught and influenced thousands of students while he was here. He retired in 2004, continued to teach part-time, and was a participant, lively participant in the mathematical life of the department, and which he participated in many activities until the time of his death in 2009. And for me, I think his generous spirit and intellect and really his profound integrity had a great impact on me and I think on many of his friends and family. Our speaker today is Martin Golubitzky, who's a distinguished professor of natural science, natural and mathematical sciences at The Ohio State University, where he also serves as director of the Mathematical Biosciences Institute. Marty is a fellow of the American Academy of Arts and Sciences, the American Association for the Advancement of Science, AAAS, the American Math Society, and the Society for Industrial and Applied Mathematics, SCIAM. He served as president of SCIAM and also on the councils of the AMS, SCIAM, and AAAS. Marty works in the fields of nonlinear dynamics and bifurcations. He's co-authored 4 graduate texts, one of which I read as a graduate student myself, fantastic. 1 undergraduate text, and 2 non-technical trade books, which I highly recommend. One is Fearful Symmetry, Is God a Geometer, which he wrote with Ian Stewart, and Symmetry in Chaos, which he wrote with Michael Field. His recent research focuses on mathematical aspects of biological applications, and I think we'll touch on some of those today. The title of his talk is Patterns, Patterns Everywhere, and let's welcome Martin Golubitzky.
Okay, thanks a lot for the kind introduction. It's a pleasure for me to be here to continue this series in honor of Professor Coe. I'd like to think that what I'll be talking about today is something that he would have found quite interesting as an algebraist. I promise that I won't talk a lot about the mathematical intricacies of algebra, but I want to focus on symmetry and the geometry that's associated with it. So really the theme of the talk is how does a mathematician use patterns? At least one mathematician in one way. And I had the fortune to be at a meeting about pattern formation a couple of years ago. And so I went around to all of the people who were at that meeting, and there were mathematicians, physicists, chemists, some biologists even, and talked to them, well, why are you interested in patterns? And the answers sort of can be summarized in 4 ways, and I'd like to take you through those. The first is that they're just pretty. So if you look at the sand dunes in the Namibian desert, you get this nice linear structure that appears, but the same kind of structure appears, oh, well, sorry. This is a mud plains. The way that this geological formation is created is that you had something that was wet and somehow over geological time it dried, and these big hexagonal patterns appeared. This is an experiment. So for the physicists, this is a convection experiment. What you have is a fluid layer that's heated from below. And when the temperature on the bottom is small, heat just conducts from the bottom to the top. But as you increase the temperature on the bottom, you get convective motion. Your water starts to boil. What happens when this transition occurs is that you get very regular patterns appearing, such as these convective rolls, but you can also get them in this hexagonal structure. So there's 2 very different physical, I'll call them experiment situations, where the same kind of patterns are appearing, but in different ways. Well, if you want stripes, you can look at the zebras, and if you want spots, a leopard. So what you end up with is that different systems, same patterns. And it's, to some extent, the role of the mathematician to figure out why there's this commonality and what that commonality is in these different kinds of systems. Okay, now those are static patterns, but patterns can also appear when time is, well, patterns that are changing in time. See whether that holds. This is a porous plug burner that Mike Gorman, who is a colleague of mine in physics at the University of Houston for many years, he worked on this experiment, and it's a pattern forming experiment. So what you have is the fuel, gas going through the burner, and this burner, if you look down from the top, has lots of different channels through it, very fractal, chaotic kind of structure. But what appears when you ignite the fuel on the top of the burner, it can be this very regular, again, symmetric pattern. Well, what about the dynamic part? And I bet that you don't know, or many of you don't know, that Acrobat Reader in its latest form will not allow you to have embedded commands. And this required a change in So these are the static patterns that appear. But you can also get dynamic patterns. And there's even a question of how do you describe these patterns. this gives you an idea that patterns can be dynamic, and we'd like to figure out how these things come about. Okay, so that was the first thing, that patterns are pretty, well, to many people, they're interesting just to look at them. But the physicists, to caricature their response to why study patterns, because there's emergent phenomena, there's self-organization. Patterns provide function, if you like, there's science behind the patterns. So what do they mean by this kind of terminology? And I'll use these big columnar joints that appear on the Snake River. They're big hexagonal columns. If you want to look down from the top, this is along the Irish coast. So they appear in various places. And you might say, well, how does this hexagonal structure form? Steve Morris, who's a physicist at the University of Toronto, did this experiment with a graduate student. And they took well, first of all, if you're not an experimentalist, does anybody know what the material here is? Cornstarch. Okay, so which is apparently a fairly standard material to use in this sort of thing. And these are the suns, if you like, and the cornstarch is put in a beaker, it's wetted, and then dried by the lights on them. And of course, how high you put the lights above this cornstarch tells you something about the speed of drying. And you can choose just the right height for which cornstarch will give you these columnar joints. So this starts to tell you a little bit about how the patterns are formed, what the science is behind. Now, another, getting to a slightly more mathematical reason for looking at patterns, it's not so much the patterns themselves, but the way patterns change as you vary parameters, they vary constants in the experiment. So in this experiment, one parameter was how high was the light above the base. That's something we can change. In the convection experiment, I talked about changing the temperature on the bottom of the plate. Well, as you change this parameter, you get a new response, a new kind of pattern. People can use this change to test whether the efficacy of a model. So let me try to explain what I mean by that. I'm going to present to you the Navier-Stokes equations. Now, I learned long ago there are two kinds of people in the audience. Those who know what the Navier-Stokes equations are, rather few I suspect, and they don't need to be told. And those who don't know, and you will learn nothing from my having written down the formula, but just to show you that there is this formula, it's Newton's laws of it's Newton's laws applied to fluid motion. And what is interesting is a little bit is the history, that in 1821, Navier wrote down these equations. 1856, Stokes re-derived them in a more mathematically rigorous way. But it wasn't until 1923, 100 years after Navier wrote down the equations, that you had the first experimental confirmation of the Navier-Stokes equations. And the question, what I want to tell you a little bit about is how did that confirmation take place? It took place by looking at a famous fluid dynamics experiment called the Taylor-Couette system. Well, if you're in England, Couette-Taylor, if you're in France, but a minor point. What this is they have two cylinders and water between the cylinders. The cylinders can rotate, the inner cylinder and the outer cylinder, they can rotate in the same direction or opposite directions. There's a variety of ways that it can rotate. Now, when it starts, if you keep the outer cylinder fixed and speed up the inner cylinder, something in the fluid flow changes. But how do you see that if you're just looking at water in the middle? So this is just have a very nice idea. These are experiments of Andrea Liu and Swinney, 30 years, 35 years ago. In these experiments, they put something called kaleidoscope into the fluid. That is, it's a liquid which has lots of silver platelets. So as the fluid is going around, if the silver platelets are horizontal and you shine a light, you'll get a lot of reflection, it'll look white. If they're horizontal, you'll get no reflection, it'll look dark. So these dark and light regions tell you something about how the fluid is flowing. And what is known is that if you start with Couette flow, that is, the outer cylinder fixed, the inner cylinder rotating very slowly, then all the fluid particles do is go around in circles with speed proportional to how close to the outer edge it is. So you get this motion. And something that you'll notice that Couette flow looks really kind of boring. There's no pattern, but it's actually the most symmetric state. A theme in this talk is that pattern corresponds to broken symmetry. You start with a lot of symmetry, and you lose a little, you start getting patterns. Okay, so if you lose some symmetry here, you end up with these Taylor vortices. And if you go into a lab and actually see this, it's just freaky how regular these things are, this pattern forms. Then there's a spiral vortex flow, and you have to imagine this in motion. The spiral is rotating. It looks like a barber pole that the fluid is going to run out the top of the container. Of course, it's only the wave that does that. The fluid actually stays inside. So what was Taylor's contribution to this? He did two things. He did very accurate experiments on when Couette flow loses stability as you increase the speed of the inner cylinder. And then he also took the Navier-Stokes equations and solved them, which is now very easy to do using a computer, not so easy to do in 1923 with slide rule and a lot of human help. But these dots are the experimental ones. The bold line is the theory, and the theory is how does Couette flow lose stability? When does it lose stability to Taylor vortices? When the outer cylinder is held fixed, so this is the speed of the outer cylinder, you end up with dead-on change. And that was considered to be the first experimental verification of Navier-Stokes. Not by any fluid dynamic properties that you might drag or whatever you could imagine measuring, but rather by a transition in the patterns. You'll notice that Taylor was quite honest. Out here, where the outer cylinder is rotating in one direction, the direction opposite from the inner cylinder, the initial loss of stability experimentally is before the loss of stability to Taylor vortices. And what actually occurs there are these spiral vortices. They are the first pattern to appear at that point. Okay, so this is all by way of background. I'd like to tell you why I study patterns, and it is because of the idea that the mathematics can describe the same kind of pattern in lots of different situations. And you get a menu for what the possibilities are, and that menu is independent of a particular experimental or physical or biological system that you're looking at. Okay, so let me give you an idea of the kinds of theorems that come from looking at symmetry breaking. If you have a system which has Euclidean symmetry, so everybody's studied Euclidean geometry. Euclidean geometry to a mathematician is the study of shapes that are invariant under translations, rotations, and reflections. And those are called Euclidean motions. So that's geometry to the mathematician. Suppose that you have a set of equations that are invariant under translations, rotations, reflections. And you start with a state that's homogeneous, it's invariant under the symmetry. Well, in the case of the convection experiment, where you have the temperature on the bottom small, there was no it was just conduction, no convection. This was a translation invariant state, rotation invariant state. Well, the theorem is that when that state loses stability, it will you will find a stripes or a spots state, which is exactly the sort of thing that I showed you before. These are the first transitions that you expect to see in such systems. Now, if you ask a question about these time periodic motions that occurred in the flame experiment, there is another theorem which says that if you have a circularly symmetric system and it loses stability to solutions that start to oscillate, then there are two kinds of states that will appear. One is what we'll call a rotating wave, where time evolution is the same as spatial rotation. So the thing just rotates rigidly. Then the second is a standing wave, and its salient feature is that it has a line of symmetry. And what I'd like to do is remind you of what the rotating wave will look like. So all it is it just looks like this thing is rotating, and that's all that's happening. And the standing wave has these lines of symmetry for all time. So symmetry distinguishes between these kinds of states. Okay, so to summarize what I've said in the first part of the talk is that in pattern formation, symmetry, or more precisely symmetry breaking, leads to a menu of possible patterns. And physics, biology chooses from that menu. The menu is model independent. It doesn't depend so much on the equations, but rather just on the symmetries of those equations. The choice of exactly which pattern appears and when, that depends on a particular model. Okay, so let's change gears. I'd like to talk about animal gaits. So this is the GAITS, and you might not be used to thinking of gaits as being symmetric, but if you walk, how would you describe that motion? If I swap my legs, I'm now a half a period off of where I would be. So think about it. You walk, swap legs, you're now where the configuration would be a half a period later. So there is this, what's called spatio-temporal symmetry in walk. Well, four-legged animals have a richer class of gaits. The Siberian susluk, everybody knows what Siberian susluk is, right? With marmot help, it's another name for susluk. And these animals, like a squirrel, bound. And what's a bound? Front, back. So it's a two-point gait, front, back. And if you look at the pattern of footfalls, every half period, the opposite, and the front legs or the back legs are hitting the ground. The elephant walked, elephants amble in English. Horses walk. It's exactly the same gait. If you can you tell what the elephant's doing with its feet from this? It's not so easy. I'll describe this as gait. There was a quiz I meant to ask you. Two-legged animals. You're talking about walking. Swap, that's a symmetry, half period out of phase. What happens, what's the motion that if you swap your legs, there's no change in the gait? Yeah, but don't ask me to demonstrate. It's a hop. Go ahead. Both legs are moving together in unison. So in this amble of an elephant, let me come back and try to explain what's going on there in a couple of minutes. I'd like to focus on a trot. So what's a trot? The horse's, let's say a horse's front right leg and left rear leg move together. The left front right rear move together, and those two pairs are half a period out of phase. Got that? Because I'm going to show you a horse trotting, and you have to see if you can figure this out. It does change going to the zoo. So can you see, would you like slow motion? So try the front leg, left leg, front, right leg, rear, and the opposite pair. And they're just hitting the ground in perfect synchrony, in a sense. So that's the spatio-temporal symmetry as a description of a trot. So even the descriptions of the patterns of motion of four-legged animals can be done with symmetry. I'll come back to that. The walk is left rear, left front, right rear, right front. Left rear, left front, right rear, right front. Just continuing. So it's a 4-count gait. You swap the left rear to the left front, to the right rear to the right front, and you have a quarter period phase shift. The trot we've talked about, the diagonal pairs of legs moving in unison, or synchrony, a half a period out of phase with each other. We talked about the bound front, rear, front, rear, front, rear. And the pace is both left legs, both right legs, both left legs, both right legs. So that's the standard gaits. A gait that you might not be aware of is the pronk, all four legs together. Well, I'll come back to the pronk. Actually, a small deer will do this, especially when startled. It's quite amusing to watch. Okay, so Ian Stewart and Jim Collins, some years ago, 20 years ago, when they started to study animal gaits, they made the observation that all of these three primary gaits of trot, pace, and walk can be distinguished by their symmetries. So in the trot, remember the diagonal legs, if you swap left legs with right legs, you're swapping the diagonals so you have a half a period phase shift. If you swap front legs with rear legs, you're swapping the diagonals, have a half a period phase shift. In the pace, remember both left legs, both right legs. If you swap left and right, half period phase shift. If you swap front and back, no phase shift. So it's different. The symmetries are different. The walk is a 4-count gait, left rear, left front, right rear, right front. Swap those legs, quarter period phase shift. So these gaits can all be distinguished by symmetry. And the question that we started to ask, and they started to ask to begin with, was, well, what can we understand where these patterns come from? And biologists have an idea for how gaits are controlled in the brain, that there is some network in the nervous system. It's called a central pattern generator, or more precisely for this, a locomotor central pattern generator. And the question is, can one design a locomotor central pattern generator to produce walk, trot, and pace? Very limited goal in this. And the answer is yes, but there's a surprise. And something, a message that I really believe in and want to transmit is that when you start working on a problem, I don't care at what level, and you do what you think the obvious thing is, and it doesn't work, then you really have something interesting going on. And that's when you should start thinking about what's happening. And so I'd like to show you here what the obvious thing is, and then we'll explain why it doesn't work. So a central pattern generator is made up of neurons. That's the presumption is in the brain. Groups of neurons. And for lack of any better information, you might as well assume that they're identical sets of neurons that are coupled together in some manner or fashion. And neurons are, by Hodgkin and Huxley, can be modeled well by systems of differential equations. So you really have a big system of differential equations. Turns out, for those interested, the Hodgkin-Huxley equations are 4 differential equations and 4 unknowns. So if you had just one neuron in each node of the central pattern generator, this would be a 16-dimensional system of differential equations. If more likely there are 20 or 30 neurons bundled together in each one, then you're talking about a system of differential equations of several hundred in number. Not such an easy thing to even write down, let alone solve analytically, let alone even solve numerically. So what I'm going to try to show you is some of the power of algebra in a rather unusual way. Suppose, just suppose, that you imagine this was the coupled system. Could such a system, which was coupled this way, so node 1 talks to node 2, and node 2 talks to node 1, and so on around the circle, could this produce walk, trot, and pace? Well, what I claim is that no 4-node network, no matter how large the system of differential equations, if they're identical nodes, can produce walk, trot, and pace in a biologically reasonable way. So let me try to explain what I mean by that. Suppose that your system, whatever it is, produces a pace. So these lines here are just to indicate that 1 and 3 are synchronous, 2 and 4, that's the left legs and the right legs are synchronous, and then they move alternately in pairs. So that's what these lines mean. Suppose that the network produces a walk. It has that 4 cycle. Left rear, left front, right rear, right front. If you apply the 4 cycle to the pace, it means that left rear goes to left front goes to right rear goes to right front, and so on. These lines go 1, 3 goes to 2, 4, or 2, 3, and 2, 4 goes to 1, 4. That is, the legs that are now synchronous are those of a trot. So the theorem here is that if a system produces both walk and pace, it will indeed produce trot, but it's a symmetry-related gait. The consequence of this is that both gaits should appear in each animal. If an animal can walk, it should be able to, if it can trot, it should be able to pace, and conversely. Well, biologists do some interesting experiments. One experiment is to take a dog. Now, dogs, especially small-legged dogs, like to trot. They don't pace. And they said, let's test them. So they put the dog in a halter. The halter forced the dog to pace, couldn't trot. And they left the dog in this halter for an hour. But being biologists said, well, 2 hours to make sure. Well, let's leave it for a day. That's not really good enough. How about a month? Well, let's go for 6 months. They leave the dog in this halter for 6 months, cut the halter off. 1 gait cycle later, it's doing the trot. So this dog didn't want to pace. Just that was not its thing. So one of the things that we know is that trot and pace don't occur simultaneously. They're not symmetric. So no 4-cell model of a central pattern generator could possibly work. And just a little bit of symmetry gives you that. So If 4 nodes won't work, we could look at 8 nodes. I won't exactly explain why look at this 8-node system, but the idea is that the central pattern generator has 2 nodes sending their signals to a given leg. Okay. Can this system give you walk, trot, and pace? And the answer is yes. There's a big math. So now there's and then there was some mathematics, or you, like the New Yorker, a miracle occurred. Then you have this list of gates that should be primary gates in the quadruped world. And we put pace, trot, and walk into the formulation. You get prunk and bound out, but there was another gate which we had never seen before, and this gate was front legs down at time 0, rear legs hit at time 1/4, and 3/4 of a period later the front legs hit. So we called it a jump. Well, just didn't mention that I spent a lot of time at the University of Houston. And the cultural season in Houston led to a real insight. So, front rear, slow motion again. Legs down, front, rear, get settled, front, rear, wait a while, front, rear, wait a while, front, rear, and so on. This was actually the guy who won that particular. That too. Okay, so Ian Stewart, who's a longtime collaborator, was visiting in Houston while we were doing some of this work. And we just went to the rodeo because we went to the rodeo. And then we started looking at each other. Hey, wait a second. This is this unfathomable gate. So I then went into a long and protracted negotiation with the rodeo. After 3 months, they were willing to give me. See, they had an instant replay, so we knew they had films. So we said, "Can we get this film?" And they said, "Well, okay, but you have to promise not to use it for commercial purposes." So I promised. This is not commercial. So once we had the film, you could figure out when the front legs hit the ground at frame 62, the rear legs at frame 75, then the front legs again at 109, the rear legs at 115, and so on. And do something that would make any right-minded statistician cringe. Just average the length of time from front to rear and rear to front into bar. If it were a bound, that would be 1. They'd be spending equal time between front and back legs. If it were this jump, it would be 3. And this is uncannily close for an experiment that had no constraints whatsoever to that jump. We later found out that some gait analysts had known that gerbils and rats would do something which is called a primitive verticane jump, which is this 3-to-1 gait. Okay, so now I'd like to switch gears yet again. I guess I should put a summary to this last thing. Notice we made a prediction about the existence of the gate without ever writing down a system of differential equations to be associated to the central pattern generator. Rather, what we did was look at the structure that these equations would have to have and use the structure, in this case the symmetries, to make predictions about the kind of gates that would be likely to occur. So it's a different kind of modeling that one normally sees in applied mathematics. Okay, so in periodic states, the gates are one way to see things. What happens if you up the ante and look at chaotic dynamics and symmetry? So let me remind you, if one says that because I have a clue whether you know this or not. Suppose that you have a mapping of the plane to the plane, so F, standard mathematical mapping F. And you choose a point in the plane Z0. Z1 is f of Z0, Z2 is f of Z1, and you can watch how these points march around in the plane. Well, let's take this mapping. Why this mapping? I don't know. We just chose a small degree polynomial and started with an initial condition, and the first 5 iterates gave you these points, and maybe the first 15, I forget, something like that, and the first couple of 100. And the question is, what do you get to see when you do this? Well, you get to see some really interesting shapes. But before I show you some of them, I want to say, well, what if this mapping had symmetry? Well, what kind of symmetry? The symmetries of an equilateral triangle or a square or a pentagon. To give you an idea as to how many symmetries does the square have? You can take the square, rotate it by 90 degrees, 180, 270, or not rotate it at all, that's 4 symmetries. And you can reflect in 4 ways, across the diagonals or across the vertical and horizontal. So D4, the so-called symmetry group of the square, has 8 elements. The symmetry group of the pentagon has 10 elements, and so forth. Now, a mapping has symmetry if it doesn't matter whether you first take a point and apply the symmetry, take a point, apply the symmetry, and then apply the mapping, or take the point, apply the mapping, and then apply the symmetry. You could do it either way and you get the same answer. And for a variety of reasons, this is the right way in dynamics to think about symmetries. So we said, it turns out that you can write out polynomials. It's easier to do in complex notation, which have DM symmetry, let M be 5. That is, let's look at mappings with 5-fold symmetry, and just took a couple of sets of constants to go into this mapping. And this is one of those eureka moments when you stick this on the computer, put in these constants because you find something, and this comes up. And you start saying, hey, wait a second. This is chaotic dynamics. And I'll show you that it's chaotic dynamics later. It's just going all over the map. Yet, you end up with pictures that, if you like a Rorschach test, everybody knows that this is a Sven. Or, in this case, it's Mike Field called Emperor's Cloak, and Mike wrote the programs to do this kind of coloring. What we're doing is starting with this mapping that I mentioned with the second row of constants, starting with initial point, iterating for 1,000 times. You really need a computer to do this. Throw those away, and then plot the next 250 million things. It really helps to have a computer. And now, look at each pixel on the screen and ask how many times is that pixel visited on this iteration, and color by number. So color means probability, likelihood that you will end up in this screen. And here's the color bar. White is very infrequent here. Red is a little less frequent. Blue is really frequent, about 1,000 times to close to 0. And notice that blue occurs almost next to white. Now, I think most of you have probably heard the term the butterfly effect. Do you know what the butterfly effect is? Oh, okay. So the butterfly effect, which I will editorialize, which is complete nonsense, is that you take you have a butterfly flap its wings in Raleigh today, and unexpectedly, 6 months later, it will snow 10 inches in Beijing, or whatever it is, whatever units they're using. So the idea is that when it is true that there is sensitive dependence on initial conditions in chaotic dynamics. That is, if you move things a little bit, then you might get a completely different set of points in your iteration. But what is less well said is that on average, exactly the same thing happens. So if I were to start with a different initial condition and do it for 250, iterate for 250 million iterates, I would get basically the same picture over again. It's reproducible, even though the particular itinerary of the point will be completely different. So there's a kind of pattern on average that appears in these pictures. Here's a third one, that third row of, this is a Rorschach test, but you may not know it, but this tests your political persuasion. And I should explain what I mean. This is the Pentagon, I think everybody knows that. But do you see what's in the corner? Do you see the White Knight or Darth Vader? So you can decide which of the Rorschach test answers you would like. This one, we tried hard to tell the Mercedes, but so I'd like to use this golden flintstone, I call it, to show you that there really is sensitive dependence on initial conditions. This has threefold symmetry, the symmetries of the triangle. It has three lines of symmetry. So let's take the plane, take these lines of symmetry and color the wedges between them. So you have 6 wedges, cyan, yellow, blue, and so on. Take a point in this region and ask if you iterate once. So in the red, in this yellow region, if I take this point, oops. If I take this point here in the magenta, it iterates to the magenta region over here. So this point goes over there. This point stays in the yellow. This goes over to cyan, and so on. You can start to see that the mapping is mixing up the plane. And if you ask the same question after 3 iterates, you start to see that the colors are getting more and more mixed. And after 9 iterates, or better yet, even after 29 iterates, you can see that any color that's appearing here has a very close neighbor that's in any of the other segments. So this is what is meant by sensitive dependence on initial conditions. And these mappings do satisfy that, and they are dynamic. Nevertheless, these pictures are reproducible, and they tell you something. If you do the same sort of thing, but not on mathematically a torus or a donut or a bagel, however you like to describe it, or you take a square and you identify the boundaries, the opposite boundaries, and iterate a map on that, you get a quilt. This is one of my favorite pictures of hex nuts, and this is by far, I don't know how this mosaic appears, but it's really quite remarkable. All of these is the same idea, iterate, a few hundred million iterates, color by number, and these kinds of patterns. So it would be, I'd like to end the talk by explaining, well, you know, even this kind of esoteric mathematics, which leads to, I think, very pretty pictures, a little bit treasures of that, but also there could be science behind it. And I'd like to use the Faraday experiment to explain it, classical fluid dynamics experiment. You take it's also called the coffee cup experiment. You take a fluid layer, let's say in a square container, and you put it on, the best thing is to put it on a speaker, and in the speaker you can send out a tone with its frequency and loudness. So the loudness is the amplitude and vibration of the speaker. The frequency is how fast it vibrates. And if you vary those two constants, you can, well, let's say you fix the frequency and vary the amplitude from very small. Well, when the amplitude is very small, it goes up and down, and the fluid layer doesn't change, it's flat. But if you increase the amplitude, then a waveform starts, and you get this wave motion, and Faraday wanted to use this experiment to study surface waves. That's the idea behind it. Now, set of physicists at Haverford, led by Jerry Gall, did some experiments. I'll show you some pictures in a moment. What they did was they took their container to be translucent. You could shine a light through it. And when the light, when the surface is concave down, the light will diffuse, and you'll see something white underneath. If it's concave up, then the light coming through will focus. So, sorry, diffuse you'll get something dark, and concave you'll get something white as it focuses. So these shadow graph pictures look like this. So just after transition, very much like the Taylor-Coulette system and the convection system that I mentioned, you get these patterns to form. There's a little bit of a difference here, but I won't go into it. But nice square, in this case you get these kind of square symmetric things. Now if you increase the amplitude of the forcing even more, then you get these very disordered pictures where if you keep taking a picture after every period of the forcing, these cells will seem to move around in a very chaotic, random way. Unfortunately, I don't have a movie of this, but it would be nice to see. You anthropomorphize by saying, I can watch this cell moving around and so forth. But it's chaotic dynamics. And what we suggested is that if you look at the intensity of the transmitted light as you, at every point in the square, that is, you start off with, how should I say, okay, this thing is going up and down. At each point, at every time, every period of forcing, you take a picture, look at the intensity of the light at every point, well, it's some approximation to every point, and average the intensity over that time. The symmetric attractors, chaotic attractors, suggest that what you'll get is something which is symmetric, but not necessarily constant. And that comes from something called the ergodic theorem. That you have, so this is just a few words, that you have a theorem which tells you how to translate symmetry of the attractor to symmetry in the average of the physical space. And this is what you get. A very nice pattern on average that is predicted by these kinds of pictures that I showed you. So what I've tried to transmit today is that regular patterns in physical and biological systems, we've gone through a number of them in geological formations, convection cells, and so forth, that's due to symmetry. The kinds of patterns that you expect to see, they can be classified independently of the model equations as long as you can identify the symmetries of the equations. And this leads to this menu of patterns, which itself leads to predictions like the jump in the force. And you don't need, this was a lecture about differential equations, and I trust you will notice that there was not a single differential equation really in the talk. Well, I guess there wasn't any, so just you know. But it's really about the structure of these equations. Thank you.
We have time for some questions. Are there any questions? Yes.
Those long things that you say were made out of cornstarch, I mean,
Yeah.
those form naturally from cornstarch?
Yeah.
Huh.
Yeah. I mean, it's a high-class physics experiment. But I think it's fair to say that physicists just love it when they can use something off the shelf to illustrate what's going on. And more than that, this is very standard for geoscientists who do this, so it's not something that really counts in that field.
Talking about the animal gates, have there been any experiments with injured animals, and if there's patterns there?
Yeah. So nothing quite as formal as your question might hope to have as an answer. But one of the things which is quite interesting is think of how a three-legged dog might move. Well, there's a theorem about the spatiotemporal symmetries of three objects is that two can be out of phase, and the third one going at twice the frequency. You say, that seems a little strange for a motion. But imagine a dog that's lost a hind leg. When it moves the front leg, it moves its hind leg. When it moves the other front leg, it moves its hind leg. So its hind leg will move twice as frequently as the two front legs. And so this is something that's seen. People have also, if you are a climber, and I am not, apparently there's some really interesting rope leg motions that are basically three-point motions that include some of the standard things that come out of that. So you do see some of the motions that you would expect from symmetry and theory in this, but what I think you were maybe hoping for is how you might be able to use this to help an animal or something like that. And this I don't know of any.
Yes, there's a question here.
So you said that the pattern emerges. Does that mean that when the pattern ends up breaking the symmetry? So you're saying that the pattern emerges when the symmetry breaks?
I'm afraid I can't hear you. So.
The pattern emerges, you said at the one point when the symmetry breaks. Is that always the case or different?
Oh, okay. Yeah. So the question was, when I made the statement that when patterns form, symmetry breaks, or what is true, when symmetry breaks, patterns form. So are there other ways that patterns can form? Sort of, but that's not typically what happens. So, and you can certainly have patterns forming.
Website you can go to if you want to help support future talks as well. Once again, thank you very much.